In this video, we'll discuss differential. So that's basically a new concept which is used to estimate the change of the function values. So let's start from this picture here, right? So this the blue curve is a function given by y equal to f of x. We fix x value, right? Any x. We make our x change a bit, which is change to x plus delta x, right? Now you can see that the function changed from uh, f of x. So this is our f of x, and this in here, this value here is our uh, f of x plus delta x. So that change, the actual change of y value will be f of x plus delta x minus f of x. We give a short notation, which is called delta y. So delta y is the difference between the function value at after you change your x minus the function value at x, right? That's your delta x. And this function value might be very hard to evaluate, right? So, so we want to do an approximation. Sometimes the evaluation is not easy. So let's sketch a tangent line. Because by our discussion, if the function value doesn't change much, wait, okay. If the function value doesn't change much, then the change of y is actual change of y is very close to the change of the y value on the tangent line, right? So this part go from here to here is a change of y value on the tangent line. We have a notation for our tangent line, which is called L of x, right? This part, we call that the change of y value on the tangent line from x to x plus delta x is called dy, right? So let's try to write down the definitions. Now you can see that if delta x is very small, dx and delta x will be very close to each other, right? So same observation as we used in the linearization, linear approximation. If the change of x is very small, this tangent line is very close to the actual curve function value, right? So let's write down definition. So our function must be differentiable because there are derivative involved, right? Y equal to f of x is differentiable. Differentiable, right? And sometimes we do not care about this function value. We care about the change of function value when you change x by a bit, right? So our change of x, we call that delta x, right? Another notation for that is dx. So this is a differential of x. So this is differential. So this is the differential of the on the independent variable, right? And so our actual change of y is delta y is given by your change of x by delta x, then minus f of x. So that's the actual change of y. Now, what's the change of y on the linearization? We know that um, uh, our line equation is determined by the slope, right? So the actual change of y should be the slope times the change of x, delta x. So which is our dy is the slope of this function at x times dx or delta x. So that's the differential, right? So you have two differentials. One is the differential of x, which is an independent variable, and the other one differential of y, which depends on the change of x. So we can see that our observation here is when when delta x equal to dx is small, then dy is very close to delta y, right? So this is a change of y value. So let's see a easy, straightforward example here. Let's see what's their difference, right? So we want to evaluate dy and delta y for y equal to x squared minus 4x when x equal to 3, where dx equal to delta x equal to 0.5, right? When you change your x value from 3 to 3.5, so what's the change of y? So actual change is easy. So actual change delta y should be half of the actual change of x minus f of x, right? We are given that x is 3, delta x is 3 point, delta x is 0.5, so this is 3.5 minus f of 3, so this is what? This is 3.5 square minus 4.4 times 3.5 minus 3 square minus 4 times 3, right? So that's our actual change of the y value. Now, what's the differential? dy, and dy we know that it is f prime of x dx, and this f prime of x is very straightforward to evaluate. So this is what's that? This is 2x minus 4, right? So this is 2x minus 4 times dx. So you can see that when x is 3, dx is 0.5, dx is same as delta x, then dy is 2 times 3 minus 4 times 0.5, right? Right. So this is 1. So the actual change, this is a good approximation for the actual change of y value when x is changing from 3 to 3.5. Okay, I can see that this differential definition for sure is come from the same observation as a linear approximation, right? So let's see example on approximate number using both methods, and let's try to compare them, right? So example here. Example. We want to use a linear approximation. And differential, right? Both linear approximation and differential to estimate the root of 1001, right? So let's try to use differential first. Differential. Right, now you can see that this number is very close to third root of 1000, which is very easy to evaluate, right? So we notice third root of 1000 is 10. So imagine you have a function which is third root of x. When x change from 1000 to 1001, you want to know what's the what's the change. We want to use the differential to approximate the change. Then you add the change to the function value at 10. So that will be the one estimate of this number, right? So that's our idea. So let's set up our function. So our function f of x equal to third root of x with x equal to 1000, and dx, differential of x, is 1, right? So that's this. So we want to evaluate the differential of this function when x is 1000, dx is 1. So that's the approximation of the change of y value. You know the change, and also you know the function value at 1000. You just add it together, right? So we know that now we know that dy is f prime of x dx, right? So from here we know that f prime of x is 1/3 x to -2/3. So this is 1/3 x to -2/3 dx, right? So when x is 1000, dx is 1, so you get dy is 1/3 times 1000 to the power -2/3 times 1, right? So that's basically the one estimate of the change when x changed from 1000 to 1001. Now you can see that we can approximate third root of 1001 can be approximated by the function value at 1000 plus dy, the change of y value, which is 1/3 1000 to the power -2/3, right? So this is 10 plus 1/3 times 1000 to the power -2/3, right? So that's one estimate using differential. So you know the function value at this number and try to plus the change of y. The change of y is given by the differential, right? So now let's see another one, linearization, right? Linear approximation, if you prefer. So the second method is called linearization. So this is our method 1, right? This is our method 2. We are using 2 ways to solve the same problem, right? So linearization is basically L of x equal to f prime of a, x minus a, then plus f of a, right? So given a function, given a value a here, a point, you can get a linearization. Now from here you can see that when our factor is when x is close to a, f of x is very close to a of x. So that's our observation, right? Here we just need to figure out what is function and what is the value of a, right? The point, the special point. By our discussion above, these both are very clear, right? We know that f of x should be the root of x. A here should be 1000, right? So f prime of x, we have done that, 1/3 x to -2/3, right? So so what? So you get f of a is 10, f prime of a is 1/3 times 1000 to the power -2/3, right? So that's something we have just calculated. So the linearization of this function at a equal to 1000 is what? Is 1/3 x to 1000 to the power -2/3 x minus 10 and x minus 1000 plus 10, right? So that's the linearization of this function. So we want to calculate third root of 1001, which is 1001, right? Which is f of 1001, right? Which it can be approximated by L of 1001, which equal to 1/3 1000 to the power -2/3 times 1 and plus 10, because 1001 minus 1000 is 1. So that's how do we use linear approximation, linearization to estimate the function value, the function value at 1001.